Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. In today's video, we're going to continue with our concepts about work and kinetic energy that we started last time, so that we are ready for the introduction of potential energy, which will happen in the following videos. Today, we will introduce a new quantity, power, that is very closely related to work. After that, we will understand when work is path-independent and conservative forces, and when work is path-dependent and non-conservative forces. So, let's start! Great, let's introduce power. First of all, I want to give some intuition about where it comes from. We all know that it is not the same to apply lots of energy in a very little amount of time, or applying lots of energy but through a very widespread time span. It's not the same to get a lot of energy in you in a car crash that happens in a couple seconds that get the same energy during a couple minutes. The result is completely different. And to quantitatively understand that, a new quantity is introduced, and that is power. If you recall, well, let's write it in black better. Power is going to be equal to the change in time, the rate of change of work. Recall, work is a quantity that in a sense accumulates. Therefore, you start doing some force, and as you continue to do the force, you have been doing more and more work. Therefore, this power is going to be a measure of how much of that force you are doing per second, per unit time. And we can see that because if our small element for work was equal to F dot dr, we see that divided by dt, this is no other thing than the force times velocity. Therefore, we see that this power is a measure of how much force you are making and how much velocity you have made the object had. It's also important to understand the units of this power, and they are really straightforward. Units of power are equal to the units of work divided by time divided by seconds, and the units of work, if you recall from last time, are joules over, are joules, that is over second, which were kilograms times meters square second square times 1 over second, which is kilograms times meters square times second cube. And this will be a very important quantity when working with energy, because lots of times if some object is using some energy, it will be using some power, and that power has to come from somewhere, and you can also find where that power is coming from, what source the power is. So it will be very useful to us using this power tool. Great. Now let's introduce path independence. Recall that work, let's do complete trajectories to understand this notion, equals F dot dr. And for example, let's examine our situation in a gravitational field with gravity G, and this is going to be our j hat and I hat vectors. The trajectory we're going to describe, it's going to be a trajectory like this. We're going to go down then to the right, then up, and then left, so that it's going to be a closed trajectory. Recall that work it's only done when the direction of the force is the same than the direction of the movement. Therefore, in these two cases, we are not going to have any work. The only relevant work will be that one made in path C1 and the one made in path C2. Therefore, let's examine what that is. We're going to have, first of all, the work made on C1 equals minus mg times dr, that is going to be dy, and we are going to go, say for example, from height y2 to height y1. So this is going to be an integral from y2 to y1. Therefore, this is going to be minus mg y1 minus y2. If we do a similar analysis to work T2, we're going to have that this is y from y1 to y2 minus mg dy, which is minus mg y2 minus y1. Now, if we try to find the total work, which as this is an integral is not going to be any other thing than the sum of these two works, we will have that total work equals minus mg. Let's take that common product out of the sums, and we're going to have y1 minus y2 plus y2 minus y1. And as we can see, all of these components cancel. This one with this one and this one with this one. Therefore, what we have found is that a closed trajectory in a gravitational field doesn't do any work. This is what is called a conservative force, because when you go around some point, you are not having to do any work. And in these cases, and in most cases we are going to treat in classical mechanics, work is going to be path independent. That means that going around this trajectory is the same thing as going around this trajectory over here. Or, for example, going from this point to this point can be done through this trajectory or this trajectory or this trajectory, because work is going to be path independent when we are treating with conservative forces. This can also be seen in the mathematics in a more straightforward way. For example, if we have a trajectory that is going up, take this trajectory, we can make it a small set of stairs in which each of these is going to be a dx and a dy in such a way that this ds component is going to be equal to a dx I hat plus a dy j hat. Now, when we put that ds or dr, they are really the same thing. On our equation, we are going to get that this is from point A to B, the force, which is minus mg j hat, times that ds, which is dx I hat plus dy j hat. We see that j hat times I hat is 0, and j hat times j hat is 1. Therefore, we get that our expression is from A to B minus mg dy. And in this case, A and B are just the final positions. So our work only cares about our initial and our final position, but the trajectory in between is completely irrelevant to the work we have done. Now, let's try to understand path dependence and non-conservative forces with friction. Once again, we're going to set up our system. We're going to have an initial x we're going to start from, and we're going to have a final x we're going to go to. And we are going to have this extra point xa. We are going to have two different trajectories. We are going to have this path, that is path 1, and we are going to have this second path that is going to be going all the way to xa and going back to xf. It's going to be called path 2. Alright, in path 1, when we are going in that direction, friction is pretty straightforward. So in this path, fk, it's going to be, let us define the I hat vector in that direction. It's going to be pointing opposite to the direction of motion. Therefore, this is going to be minus mu k times the normal force, which is going to be mg. In this first path, we're going to draw in red. Alright, then work, which is the integral of f dot dr, it's going to be equal to, this is I hat, minus mu k mg I hat times dx I hat, and it is going to go from xi to x final. From xi to x final. If we integrate this, we easily get that work is no other thing than minus mu k mg x final minus x initial. And that is the work we need to do to move this object from xi to x final through path 1. Now, let's examine what happens when we take path 2. The first part, in which we are moving from xi to xa, it's pretty straightforward. We just move in this direction, and friction is going to be the exact same thing. Fk equals minus mu k mg I hat. We carry out the exact same analysis that we did before, and we find that work 1 for the first part of the path is going to be equal to minus mu k mg xa minus xi. And now, when we are going from xa to xf, in this direction, things are going to change a little bit, because remember, friction is a force, as we saw in part 6 of classical mechanics, that always points opposite to the direction of motion. Therefore, when we are moving in that direction, friction is going to point in this direction. That means that Fk, now it's going to be plus mu k mg I hat. And now, when we do the work analysis, we're going to get, this is mu k mg dx from xa to xf. And if you solve this, you are going to get that work 2 equals mu k mg xf minus xa. And now, when you try to find the total work, you are going to get, let's see, mu k mg times positive xf, negative xa, and from here, negative xa, and positive xi. In this situation, we find that the work is not only what we did earlier, but it's going to be much bigger. Therefore, in general, friction is going to be non-conservative, because if you go back to the same point, if you go from here to here and you go back, you are going to have to do some work. And that happens because friction depends on the direction of motion. That is something that will characterize non-conservative forces. And more importantly, work is path dependent. Having different paths to go from one point to another will give you different solutions for your work. That is all for today. I hope you understood all of these concepts about work, path dependence, path independence, and also power, because they will be very useful all throughout our analysis of energy. Be prepared, because next time we're going to introduce potential energy, which is going to give all the richness that the energy world really has. I hope you liked it, and any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!